All right, welcome back to Math 160. It's always a fun day, isn't it? So we are currently on our last day of week 5. We are moving right along. We left off on page 13. So we've talked about measures of central tendency. We've talked about measures of variation. And now we're ready to talk about measures of relative standing and box plots. So let's take a look. We're going to start off by defining z-score. We talked about this last time. So let me flip back to a previous page just for a moment. Do you remember the empirical rule that we discussed on Monday? So one of the things that I wanted to comment on is the fact that these values, these numerical values, -3 to +3, these all also represent z-scores. So when we were kind of breaking this down and saying, okay, well, this is 2 standard deviations above the mean, this also indicates that it has a z-score of 2, right? So something like that. We wanted to have that dialogue so that I can get you ready for our next section. And we'll actually understand more about z-score and things like that. So let's start with a definition. A z-score is a standardized value. It's basically what lets you compare apples to oranges. When you standardize your data, you can literally compare 2 completely different populations, which is incredibly helpful to statistics. The z-score is the number of standard deviations that a given value X, a raw data value, is above or below the mean. Remember that it gives you the number of standard deviations. The z-score is not the standard deviation. I want you to notice the difference. So we were able to calculate standard deviations. And then when we're looking at the normal curve, we're trying to identify how many standard deviations away from the mean are we located? Is this raw data located? That's essentially what we're doing here. And that raw data value is assigned a z-score, which is what allows us to compare different populations, apples to oranges. The first thing I want you to consider is we do have a formula, regardless of whether or not it's for a sample or a population, the formula is the same, the notation is just slightly different. So what I'd like to do is actually write the formula in words. So you have a z-score, and the formula to calculate the z-score is when you take the raw data value oh no, the pen is bleeding. And then you subtract the mean. And then you divide by the standard deviation. That is the formula for calculating the z-score. Quick question for a sample, what's the notation for mean? I forgot.
You said the thing for the mean, like the symbol?
Yeah, what's the symbol for the mean for a sample?
Like M, like that.
That U-shaped M thing?
Is it the squiggly line thing?
Oh,
No.
Mu.
X bar.
Is it X bar? Yeah.
Yeah, the mean for a sample is X bar. I'm just going to write this again. X bar is the mean. This is for a sample. But the other one that everyone was commenting on, that mu, that Greek symbol, that's for population. So I'm just going to write that down here. So for population, mu, that Greek symbol, that represents the mean for a population. Good. What was the notation for standard deviation for a sample?
Is it that kind of lay down on 9, 6?
Oh, that's so close. That's for the population.
Mm.
I'm gonna write that right here. For the population, that's sigma. So it does look like that flattened 6, that's standard deviation. What about for a sample?
Does it have like the bar above it?
No bar, Angelica, you're correct. It's
Just
just S, yeah. It's just S, standard deviation. Now that we think about it, it doesn't seem all that creative, huh? Standard
You said
deviation.
for a sample, it's sigma, and for the population, it's just us.
No, notice here that I've written down that the sample for our mean, it's X bar, and then for our standard deviation, it's S. And then for a population, the mean is mu, and the standard deviation is sigma. So it's that flattened 6.
Okay, thank you.
You're very welcome. So that's kind of why I didn't want to write the formula in notation. I rather write it in words because the formula is the same either way. I just don't want you to freak out by seeing different symbols, different notations. No matter what value represents the raw data value? Always?
X.
Yes, beautiful. No matter what, your raw data value is your X. Good. And then your Z-score is obviously Z. Another thing to note for the Z-score, round all Z-scores to the hundredths place. Okay, so if you have a Z-score, it should actually always have 2 places after the decimal, no matter what. So as a couple examples, you can have a Z-score that's equal to 1.96. That's a common Z-score. You can have a Z-score of -2.00. But notice that in either case, I still have 2 places after the decimal. That's going to be really important to remember. All right. Take a look at practice number 6. Anna earned an 1180 on the SATs, where the mean was a 1050 and the standard deviation was 100 points. Lupe earned a 24 on the ACTs, where the mean was a 21 and the standard deviation was 2.5. Calculate their Z-scores to determine who had a higher relative score. So the first thing I would always recommend for problems like this is organize your information. Literally, I would write the following. I would say SATs. I would note that we were given the mean for the SATs. And if we're referring to the SATs in general, is this a sample data or population?
Population.
Yeah, for sure. Definitely population. So the mean was a 1050 and the standard deviation was 100 points. Good. So that's for the SATs. This is for the population of people who took the SATs. For the ACTs, and I'll just put that over here to separate the data, we see that the mean was 21 and the standard deviation was 2.5. This is actually a perfect example of how we're going to be able to standardize their scores so we can see who did better. Right now, this looks nothing alike. Like, how in the heck are you going to compare a score on the SATs versus a score on the ACTs? Well, you do that with statistics. You do that with Z-scores. So let's begin with Anna, who took the SAT. So I'm just going to write here, Anna. We're going to start by calculating her Z-score. So we have Z is equal to, we know the mean for the SATs, that's 1050. So we know that it's going to be minus 1050. I just didn't write anything here yet. I will in a second. And we know that the standard deviation is 100. I like inputting the values that were given and then realizing, oh, so we're told that Anna earned an 1180 on the SATs. That's her actual raw value, that raw data value. So it's going to be written as 1180, your raw data value minus the mean divided by the standard deviation. Good. Go ahead and punch this into your calculators. And then when you can, please give me your z-score to 2 places after the decimal.
1.30.
Yes, perfection. 1.30. So now we have Anna's standardized score. Let's work on Lupe's score. So we have z is equal to Lupe's raw data value. She earned a 24 on the SAT, so it's going to be, or the ACT, excuse me. She earned a 24, so it's going to be 24 minus the mean on the ACTs divided by the standard deviation. Go ahead and punch that one into your calculators.
1.2.
Yes, 1.20. Beautiful. We're going to tack on that 0 at the end, and you'll see why later on when we start to use charts. Beautiful. So thinking about their respective scores, let's draw a curve. I know this is your favorite thing. I know you got so good at this from last time. It's just getting over that hump, right? It's like, oh, what the heck? Draw your normal curve. Make sure your axis goes from -3 to +3. Those represent that represents kind of like a number line, right? It's your scale for your z-scores. So they're actually pretty close to each other. We see that Lupe scored a 1.2 as her z-score, so it's approximately here. And then Anna is a 1.3, so it's approximately here. So, I mean, obviously I can't smush them together, but you know what I'm saying. So clearly we recognize that Anna outperformed Lupe. So we're going to note here, and we don't need the curve to identify that, but I think a visual is nice because you can be like, aha, yeah, look at how far ahead both ladies are. So we're in this upper region here, which is actually really nice. That just implies that they did well on their tests. They're definitely above the mean. Okay, so let's go ahead and write. Anna has the higher relative score, which means, yeah, look at my brain said which, and I wrote when, which means she outperformed more of her population than Lupe. That's how you compare apples to oranges. You standardize their score. That way you can say who did better, who outperformed who. You know, what is the comparison between these two individuals or these two populations? What questions do you have on this topic, on this idea?
How did you get the 1.30 and the 1.20? Because I did the 1,180 minus 1,050 divided by 100. I got 0.013.
I know why. So punch in your numerator again in the calculator, 1180 minus 1050, then press enter, then divide by 100. What ended up happening is there was a syntax error in your calculator when you punch this in, and it didn't accept your answer the way it was intended to, like the actual syntax.
Okay, so I have another question on top of that.
Love it.
Well, I'm sorry for the truck behind me. Today's garbage day. What if you do 1180 minus 1050 in parentheses and then divide by 100
Yeah,
because this then
yeah,
because
love
of PEMDAS.
I love it. Let's do it. I'm down for that. That sounds great. Perfect, which actually is exactly what we had to do. That's beautiful. So you want to make sure if you are inputting into the calculator, you can do it both ways. You can use parentheses 1180 minus 1050, close the parentheses, then divide by 100. This way, your calculator understands exactly what you mean. If you wrote 1180 minus 1050 and then divided by 100, that syntax is wrong. What it thinks is you have 1180 and then you're subtracting just this amount. So you want to be careful, just this division, and that's not what you want, okay? So just be super careful as you punch this in.
I have a
Good.
question.
Emma,
How can you, I'm still having trouble like differencing like the sample versus population. Like in a problem like this, how can you exactly tell again?
well, for this one, notice that we're talking about Ana and Lupe, who are individuals who took tests, right? And then we're given the mean for the SATs in general. There was no indication that that was a mean for a sample of students who took the SATs. This is a mean for the SATs, period. So immediately what I want you to think of is, oh, okay, wait a second. If you know that the mean for the SATs was 1050, that's for everyone who took it, right? That's literally everyone who took it. There's no indication that the researcher took a small sample and said, hey, only you guys take the SATs, and then let me calculate your mean and your standard deviation. So that's really the big picture difference between, you know, having a sample versus knowing that you're working with a population. Does that kind of help thinking about it that way?
Yes, thank you.
You're very welcome. Beautiful. Okay, try number 7. And I want you to try this on your own. Males have red blood cell counts with a mean of 4.719. Can you see what's happening here already? Like, can you visualize, is this a sample or a population? Think about the statement that I just read. And a standard deviation of 0.490. While females have red blood cell counts with a mean of 4.349 and a standard deviation of 0.402. Who has a higher red blood cell count relative to the population from which it came? A male with a count of 5.58 or a female with a count of 5.23? Explain. Go for it. Take a couple minutes. I'm going to pause the recording while you do this. Lucy, excellent. Okay, so we're going to separate our information. We have the male blood count versus the female blood count. We know that we have a mean of 4. I don't know why I put a point there. Guys, I don't know what's going on, but my brain is completely like haywired. It's like glitching. My brain is totally glitching. And it has a standard deviation of 0.490, while females have a mean of 4.349 and a standard deviation of 0.402. So we want to know who has a higher red blood cell count relative to their population. So we'll start with the male, who has a count of 5.58. So we're using that as our raw data value. Remember, it's for a specific male. So we're going to calculate his Z-score. So we have 5.58 minus the mean, which is 4.719, divided by the standard deviation, which is 0.490. When we plug in this value, or this fraction here, we get a Z-score of 1.76. Make sure you round to the nearest hundredths place. For the females, we had a female with a count of 5.23. So that represents the raw data value. So again, let's calculate her Z-score. So we have 5.23, the raw data value, minus the mean, which is 4.349, divided by the standard deviation, which is 0.402. Punch this into your calculator, you'll find that that female has a Z-score of 2.19. Clearly, she has a higher Z-score, which means that she has a higher relative blood cell count respective to her population. So I'm going to write that down. The female has the higher relative blood cell counts respective to her population. Excellent work. This ended up being really nice because we were given the mean, we were given the standard deviation, and we were even given the raw data value. I will tell you that because you have 1, 2, 3, 4 values in any z-score formula, you have 4 values in this z-score formula. If you're given any 3, you can find the 4th. That's a hint towards where we're going to go in the near future. If you have any 3, you can easily find the 4th algebraically. Of course, that's why we take algebra for statistics or an algebra course before this class, because we need to have that foundation. So I just wanted to plant a little seed for what's to come, okay? The next idea that we have is something called the range rule of thumb. So take a look at this definition. Kelly, would you read that out loud for everyone, please?
This rule states that for many data sets, the vast majority, 95% of sample values are within 2 standard deviations of the mean. To find the minimum usual value, you take the mean and subtract twice the standard deviation. To find the maximum usual value, you take the mean and add twice the standard deviation. And usual value would be if the score is greater than or equal to, or if the z-score is less than or equal to 2.
Perfect. Notice what I'm highlighting. You may want to do the same thing. To find your minimum usual value, like what's typical, take the mean, subtract twice the standard deviation. To find the maximum usual value, take the mean and add twice the standard deviation. Anything within those bounds is usual, typical, boring. This, it seems like very, very commonplace. Anything outside of that would be rare, okay? Unusual. And we'll use that language, unusual versus usual. Let me draw a diagram so that you can have a visual so you can understand what I mean. So again, normal curve, I know. Let's go ahead. Draw your curve. And label this. Okay. I'm going to wait for you to draw your curves. That way you are paying attention to what I'm going to say right now. What I've noticed in past semesters, and this is my 3rd semester teaching stats, which is really awesome because I'm loving collecting this class as many times as I possibly can because I love teaching this class. So one of the things I noticed is that I've had issues with this part in understanding the concept behind the range rule of thumb. So I want to try to break it down a little bit differently and see if it's better, if it makes more sense in this description. Okay, first things first, you're told that the minimum usual value would be found by taking the mean. By the way, here's the mean, right? It's right in the center of the data. And then you subtract twice the standard deviation. What that means is you would be 2 standard deviations below the mean. So this would refer to a z-score of -2. Now, while that is a z-score of -2, to find the value, that usual value, you actually have to do the math. So to find the value, to find this value, you would take your mean and you would subtract twice 2 standard deviations. And we actually did this earlier in our unit. We played around with this idea to find values. We did that in practice problem number 5. When we talked about the heights of 5th graders. Can I flip back for a second? I'm going to cover this just one moment. We did that here in practice problem number 5. So notice when we wanted to find the range of values within 2 standard deviations of the mean, this actually represents the range rule of thumb. Range rule of thumb. That's within 2 standard deviations of the mean. That might be something you can add to your page 12, problem number 5, part B. So notice that at -2 and +2, we took the mean and we subtracted 2 standard deviations. That's what gave us 53 inches. And then for the upper value, we took the mean and added 2 standard deviations, and that's what gave us 61 inches. So the range would be between 53 and 61 inches would be usual, right? I'll show you on the diagram in just a second. I wanted to demonstrate that we have done this before. Okay, so going back to our diagram here, let me just finish writing out that. So this value would be your minimum, right? This value represents your minimum. So I'm going to write min here. At +2, 2 standard deviations above the mean, or a z-score equal to 2, to find this value, which is your max, you're going to take your mean and add 2 standard deviations. Notice I'm using notation for sample. It's the same formula if you were finding these values for a population. So take the mean of the population, subtract 2 standard deviations. Take the mean of the population and add 2 standard deviations. So I'll put down both formulas, but they mean the same thing. We know this. Any values, all of your data values that fall within would be usual. This would be commonplace. This is not like anything special because the bulk of the population fits within these 2 values. Okay, the bulk of the population fits within these 2 values. So that would be usual. That's usual, that's typical. You expect that your values will be within these 2 bounds. Think about it. I mean, 95% of the population fits within 2 standard deviations of the mean. 95%. So that's totally usual. If you happen to have a value above, so in this region or in this region below, so either below a standard deviation of 2 below the mean or above 2 standard deviations above the mean, this would be considered unusual. Think of this as being rare. Like if you're in the tails here, that's pretty rare. There's a very, very small percentage of the population that falls in this region, either below or above. Altogether, that's just 5% of the population. That's super rare. Does that make sense to everyone? That if you exceed the range rule of thumb, that it's unusual, but if you're within the range rule of thumb, that you are usual? Does that make sense? Ho, how's that looking? Does that make sense to you? Okay, score.
Yeah, it makes sense.
Beautiful, beautiful. All right, let's turn the page and see what's going on with this. Number 8. It has been reported that the average female will have a pulse rate of 74.0 beats per minute with a standard deviation of 12.5 beats per minute. Using the range rule of thumb, determine the minimum and maximum usual values. Okay, we are going to use the same formulas. So we are going to first note the information that we have. The average female, right? Average female, this is a population. The average female will have a pulse rate of 74.0 beats per minute. So I'm going to note that the mean is 74.0 beats per minute with a standard deviation of 12.5 beats per minute. We're going to use the range rule of thumb. So for our minimum, I'm going to write min above what I'm going to write, and it's the mean minus 2 standard deviations. So let's plug in our values and find the minimum value here. The mean is 74.0 minus twice the standard deviation, and the standard deviation is 12.5. So would someone punch this into your calculators and tell me what is the minimum usual value?
I got 49.
Beautiful. So just because we have to, it seems like one decimal place, one place after the decimal, I'm just going to add that 0. So it's 49.0, just so that we're consistent with what we have so far. I also want to write out the maximum. So we're going to write max. And we've got the mean plus twice the standard deviation. So we're going to plug into this formula. The great thing is I'm writing this out so that it's kind of cookie cutter. So you could take it and repeat it, rinse and repeat for any problems that involve range rule of thumb. Good. What about the upper bound, your maximum?
99.
Yes. So we'll write it as 99.0. So the range of usual values, we're going to write as 49.0 comma 99.0. So we're going to write this in interval notation. So the range rule of thumb, your range is from 49.0 to 99.0. Now I'm going to write a statement that tells us what this means. The range rule of thumb indicates that values less than 49.0 beats per minute, I hope you don't mind me abbreviating, beats per minute, are unusually low, right? If I have a value that's lower than 49.0, that's unusually low. While values that are greater than 99.0 beats per minute would be unusually high. Okay, the range rule of thumb indicates that values less than 49.0 beats per minute are unusually low, while values that are greater than 99.0 beats per minute would be unusually high. So in Lumen, if you're doing one of these problems, one of these word problems, and they're like, oh yeah, so you found that a female had a pulse rate of 63.2 beats per minute, would that be usual or unusual? And you would say, oh, 63.2 beats, that falls within the range, so that would be usual. If they said, what about a female who has a pulse rate of 38.5 beats per minute, you're like, whoa, that's unusually low, right? Or a female with a pulse rate of, 99.9 beats per minute, you're like, whoa, that's out here, that's unusually high. Okay, so you can think about the range of values. If you exceed that, it's unusual. If you're within those values, it's usual. What questions do you have for me that I can clarify? Wow, well, I think this semester is going to be a much better outcome. I'm very pleased. Go ahead and try practice problem number 9 on your own. It has been reported that the average household discards 185 pounds of plastic per year with a standard deviation of 22.35 pounds. Using the range rule of thumb, determine the minimum and maximum usual values. Okay. All right, so it looks like all of you have exactly the correct minimum and maximum values, which is super exciting. So I was writing a statement here. The range rule of thumb indicates that values less than 30 pounds of plastic would be unusually low. And values greater than 229.70 pounds of plastic would be unusually high. Perfect. And that concludes practice problem number 9.
I have a quick question.
Yeah, Surajini.
So anything out of that range would be either too low or too high.
Yeah, oh
Anything
yeah.
out of those numbers. Okay.
Yeah, for sure. Think of it as like extreme, right? Like if you're lower than the minimum, that 2 standard deviations, like these values account for 95%. If you're outside of this 95% window, you're either here or here, then that's pretty crazy. That's pretty unusual. That's highly unlikely. There's only 5% of the population that falls outside of this range. So I want you to be like, whoa, that's either too low or too high if you're outside of that range. And it's actually really helpful to start thinking in terms of that, whoa, like, okay, this value is either really low or really high, because later on in the semester, we're going to talk about confidence intervals. We're going to talk about a range of values where we feel confident that our data will fall within that range. If it's outside of that, then something's happening. There's something very exciting happening in the data. And we actually use that, statistically speaking, to say that there's a significant difference. There's something statistically significant happening, which again is exciting, because you don't always want to, find the same kind of data and you're like, okay, this is the boring result. We're getting the same old, same old. So it's very exciting when you have something that's like, whoa, it's outside of the norm. Okay. We'll get there. That's later. The units on confidence intervals and hypothesis testing, those are the last 2 in our course. I wanted to add this note at the bottom, but keep in mind this is not referring to the range rule of thumb. We have formulas for that. This is just a crude measurement. Think of it as like, a quick way to have an idea of what's happening. So as a crude measurement, people use the range rule of thumb to estimate standard deviation using this formula. So this is our crude measurement, okay? So standard deviation is approximately the range divided by 4. All right, so this is going to give us a standard deviation, but this is just crude. This is actually something you typically won't ever use, but I wanted you to kind of see this, okay? So for instance, let's say that we'll try to calculate the standard, I'm going to write this out. Let's estimate the standard deviation using the range rule of thumb from problem number 8. And this is just an estimate, right? So we're just going to estimate the standard deviation using the range rule of thumb from problem number 8. If I scoot up to problem number 8, you see that our range was 49.0 to 99.0. That's your range rule of thumb. This is your low, this is your high. So what we're going to do is we're going to find the range, which is you take the high minus the low. So we're going to use this formula. So for standard deviation, you're going to take the high value, subtract the low value, and then divide by 4. If you plug this into your calculator, you find that the standard deviation is 12.5, which is very cool because look at the standard deviation that we had for that problem. It was 12.5. So it's just kind of a quick and easy way to find that standard deviation. If, for instance, you only knew the range rule of thumb, that range. Not always will you be given the mean and the standard deviation. You might actually be given just that range. Let me write that down here. The range was 49.0, 99.0. Let's say the word problem did the math for you and they're like, hey, here's your range rule of thumb. Estimate the standard deviation. You could be like, oh yeah, I know how to do that. I can estimate the standard deviation by taking my high value minus my low and then dividing it by 4. So that's a good estimate. It turned out that it was exact for this one. All right. Magnifique. Magnifique. We are doing fantastic. Our next section deals with measures of position. But I think at this point, I would like to again pause. So for measures of position, I anticipate that we will end up, yes, we will end up finishing our notes on Monday because measures of position are actually pretty straightforward. They all go together kind of quickly, especially when we talk about box plots, interquartile range, you know, all those kinds of things, first, second, third, fourth, fifth, data summary values, like a 5-point summary. We'll talk about all of that on Monday. I would like to, yes, Donna, I can place.
Thank you.
Where did I put it? Where did I put you? Place. Oh, it's right here. I'll put this back on the screen just so that you can see what I wrote. So at this point, anyone who would like to try the workaround for Minitab, I want to do that with you. Okay. But other than that, everyone else, if your Minitab is working, have a wonderful weekend. Make sure you are getting your work done. Keep in mind that we are in Unit 3 right now. So actually, I'm going to share my screen and look at Lumen. Wait, don't leave yet. Hold on. Un momentito. 1 second. Okay, so Unit 3, we had homework assignments. We didn't come up with due dates for these, and I would like to. So would you volunteer some due dates for these 2 assignments? We just finished both of these.
Oh my God, there's me on the screen. The little cat.
How about next Wednesday?
Do next Wednesday, the 27th,
So,
the
yeah,
29th?
Wait. Could we maybe like, okay, so I know like Wednesday's the usual due date. Is it okay if we can maybe like push this to like Thursday, because every Wednesday I have lab and I don't leave, and I'm at MCC from 12 to 10 p.m.
Of course. How about we do Friday? Is Friday the first better?
The first.
Yeah.
Score. So that will be for that first assignment and for this assignment. So we're going to do Friday the 1st. Good. We will finish our Unit 3 notes by then. So I am going to put a due date for these the same day, because by Monday we're going to finish this. And if we need more time, we'll push these out. I will tell you that your first test is going to be on Units 1 through 3. So is this already available? Don't take this yet. Let's just hide it. I hid it.
So what do we do? Do we log into Zoom and then, is this like something we have to print out and then log into Zoom and then?
No, you just take this in Lumen. You don't have to take this proctored. You can just do it because you have 24 hours to do it.
Oh, so you can take it at any time.
Yeah. And you'll have 3 attempts to do it. So it'll keep your highest score. Each attempt is 24 hours. So I didn't want to, I wanted you to have time to get through it.
Can we use our notes? Sorry.
Say that again?
Can we use our notes?
I mean, technically, you can use anything your heart desires. I would try to do this as best you can in terms of mastering that content. But the reality is, no matter what, for all of your stats class, you would have always had a formula sheet. Like literally, you could have written anything you wanted on that. So if you want, just make a formula sheet for yourself, just so you could practice what it's like maybe being in class. Okay. Okay.
For our final, like, is it gonna be the same thing where we can take it at any time throughout the day?
No, the final is different. The final we actually have to proctor together. So we'll be taking that over Zoom in this wonderful Zoom room.
Okay, I was just wondering because I know some of my classes. Okay, so but it's gonna be, is it gonna be in person on the computer? Because I'm trying to figure out if like at what time I could like leave during the end of the semester. Because sometimes sometimes like during that time, like I leave because I go visit my family for Christmas over in San Diego, and like sometimes they're on the computer, so I just have to like sit there and take it on the computer, or sometimes you have to go in and I have to figure out when I'm gonna book these tickets.
You all registered for a remote class with me, so everything is remote, including the final.
Okay.
You won't have to come to class at all.
Okay.
I have a small question. I don't know if you know this. So in a month, I'm going to Paris,
Yes.
and it makes me just a little nervous with the whole Wi-Fi thing and MCC's Wi-Fi, because sometimes they just think that I'm like hacking or something if I'm on my phone and on a Zoom thing.
Oh,
So should I alert like the tech people if they see that there's an IP address coming from overseas? I don't know if they think that people are going to be hacking or.
Oh, aren't you in Hong Kong right now?
Oh no, I'm in South Korea.
Oh my
Korea.
gosh.
No
that's so-
way.
Yeah. Isn't that
That is
It's,
so
That's really
cool.
cool.
Yeah, it's 11 p.m. over here. So
Yeah.
What time is it over there?
11:09, like about 13 hours ahead.
Oh my
of you
God, go
guys.
to bed.
I know. He's like taking class mad late.
Oh,
Yeah.
that
my
is so
God.
cool.
So
Not
Yeah,
even
I
a
think
problem.
you'll be fine.
if he can do it in South Korea, you can do it from Paris.
Oh yeah.
That's insane. We all
I'll
just
just run
woke
the
up.
marathon and FaceTime you guys.
Awesome. I love it. I love it.
Right,
Cool.
thank you.
You're
I
welcome.
hope South Korea is great, by the way.
I want
Yeah,
to
thank you.
I want to go. Awesome. Okay, Stephanie, you have a question?
I was wondering if the test was timed.
Yeah, 24 hours.
Oh, okay. I didn't know if you can like, if there was like 90 minutes or something.
No, it's a full day. And I do that intentionally. I mean, I know that things can happen. Maybe you're really busy with work, but you could put in some time for the test and then you'll pick it up later in the day. Like, I just wanted you to have that flexibility.
So you can come back later to it.
Yeah, you can't go to, so if you are starting the test and you do questions 1 through 5 and they're like, shoot, I gotta go, you save it. When you come back, you can't do questions 1 through 5 again, right? You just do 6 through whatever. So just keep that in mind.
Okay.
Cool. All right, everyone. If you're here, it's because we're doing some Minitab stuff, but let me stop the video. Excellent work today.